the first thing we need to talk about tonight is the standard normal distribution. We've been talking about the normal distribution for a couple of days now, and all the properties that we've seen that apply to any old normal distribution also apply to the standard normal distribution. And the standard normal distribution is something that we're going to see quite a bit throughout the rest of this course, so you do need to become familiar with this concept. But first of all, we need to talk about notation quickly, because I realized we did not go over this the other day. For any normal distribution, we can use this notation to identify what specific distribution we're talking about. We use the N, the capital N, to show that it is a normal distribution. And then you'll notice that in parentheses we note the mean and then the standard deviation of our given normal distribution. And just those two pieces of information are sufficient for us to get quite a bit of information about our distribution. So for instance, if we had a normal distribution that we were looking at that had a mean of, say, 10 and a standard deviation of 2.5, this is how we would notate that particular distribution. But of course, that's not a standard normal distribution. We need to get into that. And this idea of the standard normal distribution takes us back to the concept of z-scores, which we discussed the other day, those standardized scores. Remember from our discussion a couple of days ago, we said that a z-score was found by taking the difference from each of our data points and then subtracting off the mean and dividing by the standard deviation. So we can find the z-score for any data point in a given data set as long as we know the mean and the standard deviation. So now we can actually talk a little bit about what the standard normal distribution is. The standard normal distribution is simply a normal distribution with a mean of 0, right there, and a standard deviation of 1. So if we take a look at this normal distribution curve that I've already drawn, again, I already said that our mean was 0, and our standard deviation is 1. So if I label our axes then, of course, 0 falls right in the middle at the peak. And then because our standard deviation is 1, I just have to add 1 out every unit that I move, and then subtract 1 for each unit to the left that I move. So what this means is that if I have moved 1 unit to the right, then I have moved 1 standard deviation above the mean. If I move 1 unit to the left, then I have moved 1 standard deviation below the mean. And if you think about that 68, 95, 99.7 rule that we talked about the other day, that would mean that right now, based on what I have shaded in, that should comprise 68% of our data. If I move out 2 distributions from the mean, or standard deviations from the mean, excuse me, then I move out to these points on the left and the right, and so what I have shaded now should be about 95% of our data. And then if we move 3 standard deviations away from the mean, that moves me out here and out here, and that should be about 99.7% of our data. So of course, as you can see, that means that we have an extremely small number of data points that could possibly be left over if we are a full 3 standard deviations above and below our mean. So that's just the general idea behind the standard normal distribution. Now what you're going to have to use this for is several calculations. Often you'll be given just a regular old normal distribution, and you'll convert it into a standard normal distribution so that you can use these calculations. Anytime you're trying to do a calculation with a standard normal distribution, you have 2 choices. You can either use a standard normal table, or you can use the calculator function that's built into your calculator. We'll talk about the calculator function and how that works tomorrow in class, but for now I want to give you a quick look at a standard normal table so you understand how those operate. If you have your textbook with you, if you open up the front cover, there's the standard normal table right on the inside of the front cover of your book. So what you should see there is a table that should look a little bit like this. Notice that on the leftmost column At the very top, it should say Z. Oops, can't even see that now. There we go, Z. And below that, what you have are various z-scores that are shown to 1 decimal place. And then if you look across the top of the table, you have values that range from 0.00 up to 0.09. So the numbers that run across the top of the table, when added on to the numbers that run down the left column of the table, give you the various z-scores that you're looking at. So for instance, if we were interested in a z-score of, say, I don't know, negative 2.13, then what I would do is I would look down this leftmost column until I saw the negative 2.1 line, which is right here, and then I would move over to the row that has 0.03, which is right here, and then the intersection of that row and the column gives me actually the probability the probability that a point in our distribution is at a z-score of negative 2.13 or below. Now that might sound a little bit strange, but once I draw a few diagrams, this should make a little bit more sense. But I just want to walk through one more example of how the standard normal table works. You'll notice in your book, and also on this table that I'm showing you right now, the z-scores are split into positive and negative scores. So for instance, the table I'm looking at right now just has negative z-scores. I'm going to move on to the next slide. And this has the standard normal table for positive z-scores. The standard normal table in your book works the same way. On one side of the page, it shows the z-scores, the positive z-scores, and on the other side, it's the negative z-scores. So let's say, for this example, I want to look up the value from the table for a z-score of 0.87. So again, I start in the leftmost column, and I'm going to go down to the row that has 0.8, which is right here. And then I'm going to scroll over, and I'm going to look across the top of the column headings and see which column contains 0.07, which is here. And then the value that I'm interested in getting from the table falls at the intersection of that row and that column, and that's this value right here, 0.878. So what that says, and again I'll explain this a little bit more on the next slide, is that 80.78% of our data in the distribution will fall at or below a z-score of 0.87. So let me go back a couple slides, and we'll take an example, or take a look at this example I've plotted. So here's our standard normal curve, which of course means that our mean is at 0, and we have a standard deviation of 1. Now in this particular case, I've drawn in a z-score of negative 1.2. What I want to do is I want to figure out what percent of our data is going to fall below this z-score of negative 1.2. So again, there are two ways to do that. We can either use the standard normal table, like I just showed you how to do, or we can use our calculator. Again, I'll show you how to use the calculator in class tomorrow. So let's use the standard normal table for now. Again, our z-score that we're looking for is negative 1.2. I'm going to erase everything from this slide. Oops, that was bad. Just kidding. Give me 1 second. All right, we're back up and running. So let's find our z-score of negative 1.2. So I'm going to go down the left column again, and I'm going to look for the row that contains negative 1.2. And because there is no digit in the hundredths place, of course, it's just 0. So I look in this first column, and the value that I'm interested in is this intersection here at 0.1151. So let me go back to the diagram. That means that here, this area that I've shaded is 11.51% of the total area underneath the curve. Because we remember when we defined density curves, we said that no matter what type of density curve it is or what type of distribution we have, the total area underneath the curve has to be 1. So if we're talking about that in terms of percentages, that means, in this case, I've got 11.51% of the area under the curve that falls to the left of my z-score of negative 1.2, which means then that I can figure out how much is going to fall to the right, of course. That's just going to be 1 minus 0.1151, and that looks like 88.49% to me. So just keep in mind that the area underneath the curve, even if it's a standard normal curve, has to add up to 1. And the percentages, or the values that you're extracting from the standard normal table, are the percentages of your data that would show up to the left of your z-score. Always keep that in mind. You're always taking the area to the left, not to the right. And the reason I'm emphasizing that is so we can take a look at this next example. So I want to know what proportion of observations from the standard normal distribution will be greater than negative 0.46. So that negative 0.46 is the z-score that I'm interested in. Anytime you're trying to answer a question like this, I would always draw a picture. So at least for me, I'm a very visual person, and the picture helps me out quite a bit. So here's a normal curve. We know that we're going to use the standard normal curve, of course, with a mean of 0. And the z-score that we're interested in is this negative 0.46. So that's going to be a little bit to the left of 0, but not too far away. So maybe right about here. Now, in order to figure out what proportion of observations are greater than negative 0.46, of course, that means that I'm trying to figure out the area that is to the right of that z-score. Well, that's lovely, except that I can't get that number directly from our standard normal table. The only thing that we can get from that table is the area that is to the left of our z-score, which is still okay, because we know that our total area has to add up to 1. So let's go back to our standard normal table, and we're going to get that z-score, or we're going to get our proportion that corresponds to negative 0.46. Get rid of these markings. Bear with me for a second. Okay, so for a z-score of negative 0.46, same process that we've been going through. Look down the leftmost column first. I'm going to find the row that contains negative 0.4. And then I'm going to look across the columns at the top and find 0.06. And then the intersection of those 2 points looks like 0.3228. So going back to our diagram, that means that the area under the curve to the left of our z-score of negative 0.46 is 0.3228. So that tells me that 32.28% of the observations from the standard normal distribution falls below a z-score of negative 0.46. But that's not what the question that we're interested in is asking. We want to know what percent of scores are greater than a z-score of negative 0.46. But fortunately, we are very clever and we know how to do this. So we're just going to take 1 minus 0.3228, and that ends up being 0.6772. And so that is the proportion of observations that fall above negative 0.6. And you can kind of tell from the diagram that it should be about 68% or so.